Dr. Saurav Chakrabarti, working as an associate professor in the computer science group at the Chennai Mathematical Institute, Tamil Nadu. Before joining Chennai Mathematical Institute, he was a postdoctorate at the Algorithms and Complexity Department of CWI, Amsterdam, Netherlands. He was a postdoctorate at the Computer Science Department of Technion, Israel. He was awarded PhD in Computer Science from University of Chicago. His area of research is theoretical computer science. His focus has been in the classical and quantum complexity of Boolean functions, including property testing, sensitivity, block sensitivity of Boolean functions, and quantum database search in electronic commerce, in graph algorithms, and in coding theory. He has published several research papers in both national and international journals.
Welcome to the UGC lecture series in computer science, and the topic is algorithms. So, today we will be looking at some more sorting algorithms, and in particular we will be looking at quicksort, and then we will see how we can improve the quicksort, and then we will look at the randomized quicksort. To start with, the problem in hand is we have been given a set S of integers, and we want to output a sorted list of the elements in this set S. For example, if the set S is something like this, which is 1, 4, 2, 10, 5, 8, 15, 13, 7, 8 and 1, it is a set of integers which are not sorted in any way, and we want to sort it in an ascending order. So, we want to output something like this, which is 1, 1, 2, 4, 5, 7, 8, 8, 10, 13, 15. Note that this is a sorted list. One thing to note here is that this integers is nothing special. You can use any set of objects which such that there exists a total ordering or proper ordering on this set of objects. For example, one can use some real numbers or can use words with the lexicographic ordering and so on. The numbers are used just as an example to show the various algorithms. So, in the last class or last lecture, we were talking about the sorting algorithms, and sorting algorithm is in fact one of the most popular algorithms in this field of computer science, and there are lots and lots of sorting algorithms. These are just a handful of them that I picked up, and we will not be doing all of them. In the last lecture we saw the insertion sort, and today we will be looking at quicksort, and we will try to understand which one is better in which setting. So, in insertion sort, the main goal was to sort the elements in an ascending order, and here was the simple pseudocode for the insertion sort. The basic idea was you pick an element from this set and insert into a already sorted list, and you keep on doing it until the elements of the S is completely exhausted and everything goes into the new array. And we saw last time that we can somehow reuse this space in the set S, and thus one can obtain by insertion sort the sorted list in runtime, which is around n square plus 3 n by 2, and space complexity which is log n. The question is that can one do better than this while maintaining the same space complexity? Note the space complexity better than log n is something hard to imagine, because when we have to access the elements of this set S, we have to maintain the registers like I, j and so on, and even those registers have log n space, requires log n space. Thus, space complexity log n is kind of the optimal one can think of. The idea is, can one do better than in the case of runtime while maintaining the same space complexity? To start with, let us look at a most obvious idea that one can have, and that is the idea of quick sort. In fact, this is some idea that one might have used a lot in their real life situations. For example, when you have in your school, when a lot of people are standing in a queue and the teacher wants to somehow sort all the students according to height, they would have picked a random person from there and try to find out, oh okay, you are standing here, whoever is shorter than this person will stand in the left, and whoever is taller than this person will stand in the right. That is a typical thing to do. And then you have a set of elements which are standing left of this person who are shorter than this person, and you want to sort this set recursively in some sense. So, for example, here, so the idea is to pick an element x from this set S, and we call that element the pivot. Now, once we have picked up the pivot, we will keep all the elements that are less than x to the left of x, and all the other elements which is greater than or equal to x to the right of x. And now, we will sort each of these elements in the left of x and the right of x recursively. That is basically the idea of the quick sort. Say here is an example. Let us S be this set which is 12, 4, 2, 10, 5, 8, 15, 13, 7 and 8. We put this first element down somewhere, and now from this set S we pick out all the elements that are less than x and put it on the left of x which is 12, and all the other ones which is greater than or equal to 12 on the right of 12. So, that is here is the split, like clearly 4, 2, 10, 5, 8 and 7 are all the elements in this set S which are less than 12, and 15 and 13 are the two elements which are greater than 12, and you put it on the right. Now, all we need to do is we take the elements in the left and sort them. How do we sort them? We will recursively call the sorting algorithm, and similarly we do for the one which is on the right of 12. And note now that I have this set of elements in the left which is sorted and less than 12, and elements which are on the right of 12 are also sorted, and thus this whole set becomes a sorted list. The key to this point is that we have taken this 12 and we have split this set in such a way that if we manage to sort the elements in the left and the elements in the right of 12, the elements will anyway be sorted. So, here is the simple pseudocode for this quick sort algorithm. Of course, if the set size is 1, there is nothing to sort. So, we have to output this set S. Otherwise, we initialize two sets R and L, both of them are empty for now. We pick the x to be the first element in this set S, and then we just basically this whole while loop is just what it is doing is that it is going through this whole list of elements in S and finding out which element should go to the right and which element should go to the left. In other words, if some element is less than x, it should go to the left. If it is on the right of x, greater than or equal to x, then it should go to the right. And once that is done, then all I need to do is that I want to sort this left side L, then I output the element x, and then I output the sorted list of R, and this total thing combined will give me the sorted list of all the elements in the set S. The algorithm is a recursive call, and thus proving the termination and correctness of the algorithm can be a bit tricky. Also, we will need to look at the running time of this algorithm. So, the correctness of the algorithm is that since I have removed one element x from this set already. So, either the size of S L or size of R will be strictly less than size of S, because one element has already been taken away from this list. And when this set size becomes 1, the algorithm anyway stops. So, every iteration the size of L plus R will go down by 1, and thus it will stop at some point. The correctness of the algorithm follows by induction, because let us assume by induction that quick sort L gives the right answer, quick sort R gives the right answer. In that case, every element in quick sort L is less than x, which is less than every element in quick sort R, and thus what we obtain is the correct output. Now, we come back to the time complexity of this algorithm. So, let us T n be the time complexity for sorting the set of n elements. This technique that I am going to show now is a very typical technique used in algorithms, and it is called recursion or recursive. So, let T n be this time complexity for sorting this n elements. Note that this while loop here, which is computing the R and L, that requires n steps, because that goes over all the elements in S and either puts them in L or in R. So, that requires n steps. So, thus how much is T n is? For T n, which is in this case a set S, it is the time complexity is it has to do this n operations, and after that to output it, it has to quick sort L. Now, to quick sort L, how much time will it take? This will take T size of L, and how much will this quick sort R take? See here size of L, because size of L is the number of elements in set L, and T n is the time complexity for sorting this algorithm, sorting this set S, set L. Similarly, this quick sort R will take T size of R steps. So, I have n steps here, T size of L steps here, T size of R steps here, and that is T n. And in other words, we have T size of S is equals to n plus T size of L plus T size of R. So, again to recap, if T n is the time complexity for sorting this set of n elements using quick sort, then we have this n elements, that n steps that has to be done, and then we have T of size of S is equals to n plus T of size of L plus size of R. But now, in the worst case, size of L can be 0 and the size of R can be n minus 1, because one element is always removed from S. So, size of L plus size of R is strictly less than n. So, what we have is that T of n equals to n plus T n minus 1. Then we can keep on doing it. So, T of n is n plus T n minus 1, which is n plus n minus 1 plus T n minus 2, and you keep on doing it, you get T of n equals to n plus n minus 1 plus dot 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 till 2 plus T of 1. T of 1 is 1. So, we have the summation of all the elements from 1 to n. So, T of n becomes n into n plus 1 by 2. Thus, this gives us the time complexity for the quick sort. Let us take a small break now. After the break, we will talk more about the quick sort. Welcome back after the break. Before the break, we had taken a look at the quick sort algorithm, and we saw that the time complexity for quick sort is n into n plus 1 by 2. Now, let us look at the space complexity of the quick sort algorithm. For the space complexity, note that we will have to store the set L and the set R, and since we have to store the set L and the set R, so the space complexity must be size of L plus size of R, which is around n minus 1 or n. So, in summary of quick sort, it does correctly sort the set S, it has time complexity n into n plus 1 by 2, and it has space complexity n. Now, recall that in the insertion sort, the time complexity was also something similar to this, it was n into n plus 3 by 2. So, this is not some massive improvement from the insertion sort, but the space complexity was log n in that case, and this is n. Now, if you remember what we did in the last lecture, after we had seen the most obvious insertion sort algorithm, we could see that we can reuse the space in some way, in such a way that we did not have to use the whole of the space n. Instead, we could do it in log n space. Can we do something similar in this case? And here also we can do something similar. Let us see the example here. I will not be doing the pseudocode of this algorithm. I will instead explain this algorithm using this example, and it will be a question for you guys to go back and write the pseudocode of this algorithm and prove the correctness of it. So, let us start with the set S. The set S, let it be this form 11, 4, 2, 13, 5, 8, 15, 13, 7, 8 and 12. Now, the pivot element is 11. So, what we do is that we first take the pivot element. Note that our goal is to find out the right place of 11, so that every other element which is less than 11 should be on the left of 11, whereas every other element that is greater than 11 should be right of 11. So, first thing we do is that we swap 11 with the last element. So, in this case 12 goes there and 11 goes here. Now, we will always mark using red the lowest index of the number that is greater than or equal to 11, but not 11. Note that 11 is anyway sitting in the end. So, we do not have to worry about the 11 for now. So, for now we should just look at this set from 12 to 8, and 12 and the red will always mark the lowest element, and green will also mark the index we are looking at. So, at this moment of course, we are looking at 12 only. Now, so let us look at the next element. The green moves one step to the right, and we have started looking at number 4. Now, 4 is clearly less than 12. So, what we do is that we swap 4 and 12, and while we swap it, we will move this green marker to the next step, which is 2, and the red marker stays here. Now, 2 is the thing that we are looking for and looking at, the index we are looking at, and 12, as we told, is the index of the smallest number greater than 11. Again, when we are looking at 12, we see that this 2 is less than 11. So, should be in the left of 11, but there exists a red marker which is left of that. So, we will just exchange 2 and 12. Thus, we swap 2 and 12 and we make 13 our next marker. Again we come to 13, and when we come to 13 we find that 13 is good, no problem, because 13 is greater than 11 and does not have to be moved. Then we move to 5. When 5, we are marking 5. So, one thing to note is that when whatever green marker is we have, anything which is on the left of the green marker has two proper divisions. A division here, which is 12, the red marker and above. So, red to green marker, everything is greater than or equal to 11, and anything which is on left of 12 is strictly less than 11, and this is what we will maintain all the time. And when we are looking at 5, what do? We will first push the green marker to the 8, swap 5 with 12, because 12 is the first element which is greater than 11. So, we will swap 5 with 12 and we push the red marker to 13. So, we have swapped 5 with 12, green marker goes to 8 and we have pushed the red marker to 13. Note again the same thing happens. Here is the green marker and this is the set. We have been split into two parts. What is it? The red marker to the green marker is greater than 11 and this part is strictly less than 11. Again we move from 8, this green marker, we find that this is less than 11. So, this has to be swapped. So, we swap 8 and 13, the red marker moves to 12 and the green marker moves to 15. Now, when we are at 15, again we see that okay, 15 is greater than 11. So, no need to worry. So, let it be. We move the green marker to 13 and similarly we keep on going like this till at some point of time we come to this stage where green marker has basically finished its stay. We have the 11 which is the pivot, we have this list which have been split into two parts, 15 or red marker and right of it is greater than 11, anything left of the red marker is strictly less than 11, and all we need to do now is to swap 11 and 15, and thus if we swap 11 and 15 we get 11 goes to the pivot and we have split this set into two halves, which is one is less than 11, one is greater than 11. So, I will not do the pseudocode of this algorithm, but I will leave it as a question to write the pseudocode of this algorithm to prove that this algorithm is right. So, to summarize this improved quicksort algorithm, we saw an algorithm which sorts the set S. The time complexity is n into n plus 1 by 2. It is exactly similar to the earlier one that we did, and the space complexity, we have not used any new space. We have done the splitting this set S into these two parts greater than x and less than x right in that set. So, in some sense we have not used any extra space, and the space complexity is only that amount of space that is required to store the indices. So, the space complexity is log n. Thus, in regards to the set of parameters, this improved quicksort is exactly same as the insertion sort. But when it comes to reality, it is found that quicksort has been used extensively in real life, and also it has been found that it does perform better than many other algorithms, and in particular it performs better than what is theoretically predicted. So, what is it that we are making the mistake, or what is happening in real life? The fact is that we can tweak the quicksort a little bit to make it randomized algorithm. So, note that in the quicksort algorithm we started with picking this pivot x, which was the first element of this set, and then we went ahead and splitting this set S according to the pivot. But what happens if instead of picking this set x as the element x as the first element of S, we pick a random element from S. So, we toss some coins and use our randomization or any of the random generators from the computer to pick a random element from this set x. In that case, what can be showed is that the expected running time is less. So, what can be shown is that it is true that even in this algorithm the worst case running time is still n into n plus 1 by 2. So, in the worst case we can be stuck with making n square plus n by 2 number of steps, but the expected running time for any set S goes down to n log n. Note that n log n is much better than n square, because log n is very small compared to n. And what do I mean by the expected running time? For people who are familiar with probability, this is the expected running time where expectation is taken over the random coin tosses. And for people who are not familiar with probability, this is just the average over all possible set S, the average running time. So, in some sense most of the time the algorithm will stop only after n log n steps. So, although quicksort in terms of worst case analysis is no better than insertion sort, but in terms of the expected running time quicksort is much superior than insertion sort. So, here is a comparison between the insertion sort and quicksort. Both of them correctly sorts a set. The worst case running time in both of them are similar or same. The space complexity in both of them are same, but while insertion sort cannot make use of randomization to improve itself, quicksort can do a lot better. Using randomization, it can push its expected running time down to n log n. The next question is, can we do something better? For example, can we have a sorting algorithm where the worst case running time is n log n and not just the expected running time? And we will see this algorithm in the next 1 or 2 lectures. To summarize, we have the quicksort algorithm for sorting, and then we looked at the improved quicksort algorithm, where the parameters was identically to the insertion sort, and then we saw that if we do a randomized quicksort, then the expected running time of quicksort goes down significantly from n square to n log n. So, this brings us to the end of this lecture. We will come back next lecture to see more better sorting algorithms. Thank you.